Hello everyone and welcome back to the final weekly tutorial video for Stat 231. Congratulations for making it to the end of term. In this last week of new content, we started to provide some tools for asking questions related to causation and gave a brief overview as to why it can be hard to answer questions of the form, does X cause Y? I believe that this material is a great way to end an introductory statistics course as it gives a peek as to what comes next and where some of the interesting challenges in statistics are. If you do go on to take more statistics courses, there are plenty of interesting ideas that grow out of these concepts that have been covered in this course. In today's video, I want to try and pull together many of the concepts that we have been learning throughout the term applied to a highly relevant topic of interest, the AstraZeneca COVID-19 vaccine. This discussion is motivated by an excellent question on Piazza, and while the answer given there is quite detailed, I wanted to take some time in today's video to use that as a way of pulling together the course concepts. It's my hope that this serves both as a good review of the content that has been covered this term, and also demonstrates that the ideas that we have been talking about have some real-world applicability. Before we get to that discussion, there are two more discussions to have first. I want to start today's video by going over the examples that I promised to discuss in last week's tutorial video. In particular, there are 4 examples which apply chi-square tests that were discussed last week that I'd like to discuss. We are going to be using that framework to answer: does the Lotto 649 appear to have any bias in the numbers that show up? Do movie genres matter for Oscar nominations? Is a Poisson model appropriate for the number of goals scored in a hockey game? Do certain athletes perform better on certain days of the week? After we work through those examples, I would like to take some additional time to discuss how we can determine the number of degrees of freedom for these chi-square tests. I will not be saying anything new in this regard, but just want to re-emphasize the key points. To answer these questions, we will consider using some data, all of which should be posted on the course website. I'm going to pop over to my computer now so that we can take a look at some R code in order to answer those questions. Okay, so we're going to take a look at a few examples that have to do with the chi-square tests that we talked about in last week's tutorial. So all of this data should be available on the course website in case you want to take a look at it for yourselves, but I'm going to just walk you through the R code that I would run to analyze some of these hypothesis tests. So the first data that we're looking at is from the Lotto 649. So in case you're unfamiliar, the way that this works, it's a lottery where each week you pick 6 numbers between 1 and 49, and then if you match all of your numbers, you win a bunch of money. The Lotto 649 numbers that have been drawn since the lottery was started, which I think was something like 1982, are all available online. So I've gone ahead and downloaded them and saved them into this Lotto 649 historical file. So I'm just going to read that in, and we can take a look at what these data look like. So if I just view the lottery data, you can see that we have the date and then the 6 numbers, and there's always a bonus number in the lottery as well. So you can see that this is up to a couple of weeks ago, and if we scroll all the way down to the end, it started in 1982. So the question that we're interested in answering using the chi-square test is, are these data really being drawn randomly? So is there a uniform representation of all of the numbers from 1 through 49? What I'm going to do is I'm going to just take out those 6 numbers that are drawn each week. I'm going to add them to this numbers vector here. And we can see that since 1982, there have been 23,256 numbers that are drawn. And we want to know, are they uniformly selected? And so one way that we could do this is to think about the null hypothesis as being theta j equals 1 over 49 for all j. And if we take this to be our null hypothesis, then we can define the expected count to be equal to the length of the numbers, so that's this 23,256 number, times by the probability that we would observe if they're being uniformly drawn, which is 1 in 49, because there are 49 numbers. And so then what we should expect is that since 1982, we've seen every number appear approximately 475 times, 474.6122. Now we can grab our actual counts just by using the table function on that vector. And so I will come down here, define the actual counts, and This isn't going to be super useful to look at directly, but you can see that the numbers 1 through 49 have all shown up, and they're 400 and change. Some of them, number 20 has been drawn 503 times, 45 has been drawn 530 times. We can ask whether these actually appear random. So once we have our actual counts, the expected count is the same across all categories. So we can define our test statistic, and that's going to be 2 times the sum, where we take the actual counts, multiply that by the log of the ratio between the actual counts and the expected count. And again, expected count is constant across all of our categories here. And if we run this, we can take a look at what that output is going to be, and we can see that it is roughly 48. So then, in order to compute a p-value from this, we need to know how many degrees of freedom are there. In order to find the MLE in this situation, we would need to estimate 48 parameters. So that's 1 parameter for each of the first 48 numbers, and then we know that the 49th one can be found by taking 1 minus the sum of the first 48. If the null hypothesis is correct, then we actually have 0 parameters, and that's because we know that if the null hypothesis is correct, each of them are equal to 1 over 49. So there's no parameters to estimate there, so our degrees of freedom, if we take 48 minus 0, that's going to be 48. Now, of course, you can also get this as k minus 1 minus p. P in this case is 0, k is going to be 49. And so then that's 49 minus 1 minus 0, or 48. And so if we just call the chi-square distribution, we can see that the p-value of this test is roughly 0.47. So probably not very significant. There's not a ton of evidence. Now this, in theory, works. We can see that because the expected count was sufficiently large, about 474, there's no reason to suspect that we need to collapse categories on the basis of the at least 5 in the expected counts. But we did say in this course that we typically want to have 10 or fewer categories to work with. So what I'm going to do now is I'm going to redefine these categories, and I'm going to say that the first 5 numbers we want to take as category 1, the 6 through 10 we'll take as category 2, and so on, up until the last category, which is 46 through 49. So note that this last category actually only has 4 numbers in it, not 5. And so we can get these through this command here, where I'm taking the integer division with 5 and then adding 1 back onto it. But so if I call this collapsed counts here, you can see that the collapsed counts now go 1 through 10. And you can see that again, roughly we see approximate uniformity across these categories, where we would expect that this last category is slightly less than the remaining because of the fact that there are only 4 numbers being represented there. Now to get the expected counts, it's no longer going to be 1 in 49 for all of them times by the length of the numbers. Instead, the first 9 categories are going to have probability 5 out of 49, and the last category is going to have probability 4 out of 49. So that's because, again, we're just counting up how many numbers are present in these groups and working our way from there. And so if I run this, I get our expected counts, and once again, we can see that the expected counts are the same for the first 9 groups, and then slightly less for the last one. We can compute the test statistic, same as we did before, 2 times the sum, where we take the collapsed counts now, and divide by the expected counts, and our test statistic is going to be 17.24. And now we want to run this as a chi-square distribution with 9 degrees of freedom. And why? Well, we have either k minus 1 minus p, where k is 10 and p is 0, because under the null hypothesis, everything is exactly specified, or you can view this as there are 9 parameters under the MLE, 0 parameters under the null hypothesis. In any event, if we run this, we see that we actually get a fairly small p-value, about 4.5% or so. So that's kind of interesting. The idea being that there's slightly stronger evidence against uniformity when we collapse down to the counts in groups of 5. And, that might be something that's worth playing around with. I'm highly skeptical that you're going to find some way to hack the lottery with something like this, but, perhaps that's a fun thing to be looking at when you're practicing for your Stat 231 final exam. In any event, you can see that in either of these cases, it's a fairly straightforward process to get to our p-value. So let's take a look at the next example. And here, what I wanted to do is take a look at some Oscars data and ask whether the genre of movie matters for whether or not movies are nominated for Oscars. So again, this data file is available on the course website, and I'm just going to read it in. Now, to describe what's happening in this data, what I've done is I downloaded a list of all of the Oscar nominees that I could find, and then I went through and tried to find the genre of each of those movies from IMDb. Now, I was only able to match some number of them, so the only movies that are left in this file are those that I could match to a genre for. So that's about 1,200, 1,300 movies here, but that's enough to play around with. And so the questions that I wanted to answer were, does the genre of movie matter for whether or not a movie is nominated? And does the genre of a movie matter for whether or not the movie wins? Now, there's one slight problem with the data that I have versus the questions that I want to answer, and that's the fact that I did not actually get any movies that were not nominated for Oscars. So if we really wanted to answer this first question correctly, what we would want to do is take a look at all of the movies that were released in a year, and then categorize them as to whether or not they were nominated for an Oscar, and by their genre. And then we would want to test whether those two factors were independent. Because I didn't have any movies that were not nominated for an Oscar, we can't do exactly that, so we're going to have to ask a slightly different question. Now, what we're going to ask is, of the movies that were nominated for an Oscar, is there any difference between the genres that they are? So it sounds like a similar question, but it is subtly different, and you can kind of think about it as we're conditioning on the fact that they've already been nominated for an Oscar. So in order to do that, what we want to take a look at is the actual counts, which we'll grab from the table of the genre field in the Oscars, and the expected counts. Well, if there is no difference, then what we should see is that each of the genres has an equal probability of being nominated for an Oscar. There are 11 genres, and so we should see that 1/11 of each of the Oscar nominations should go to each genre. So we can take that in as the expected counts. We compute our test statistic just as above, and then we can compute the p-value using our p chi-square function again. Now here, the degrees of freedom that I have specified are actually incorrect. So let's take a look why. So the actual counts for the nominations, we can see that we have all of these genres here, and if we do a quick counting out of them, we should see that there are 11 genres. That's why we use this 1/11 as the probability for the expectation. But of course, in a multinomial model, we only need to estimate k-1 of the parameters under the null hypothesis. So that should not have been 11 degrees of freedom, that should have been 10 degrees of freedom, a lower tail false. And if we run that, we can see that the p-value is 0, right? And just to check, if you had used 11 degrees of freedom, you would have gotten the exact same thing. And that's because if we look at these actual counts here, they're very clearly not uniformly distributed. You can see that there are 328 that are categorized as a biography, and there's only one under the mystery. So it's pretty evident that those are not uniformly distributed if we had just looked at them. But in any event, we can compute the p-value. It is 0 or a rounding error of 0. So let's look at the perhaps more interesting question here, and that's, do the winners of the Oscars differ based on the genres? Now here, what we want to be doing is actually generating a two-way table, and that's one of the factors is going to be the winner of the Oscar, and the other one's going to be the genre. So let's create that table here and take a look at it. If we output this table here, you can see that true would be for the winners, false would be for the losers, and then we're broken down by the different genres. We're going to run into some issues with our needed expected counts being 5 because of these genres which have fewer observations within them. Right, so what I'm going to do here is I'm actually going to redefine the animation, documentary, fantasy, horror, and mystery to just be an other genre. So we have 6, 1, 1, 3, 1. respectively. So if I do that and I redefine the actual counts here, we can output this now as this more simplified table where we just have this other to contend with. Now, in the data set, 258 of the movies were winners, and we saw a total of 258 plus 1,015 non-winners, which means that our estimated winning probability is going to be 258 divided by 258 plus 1015, or about 20%. Roughly 1 in 5 of the movies that were nominated for an Oscar won an Oscar. Now, it's worth noting here that I have not gone through the hassle of filtering down to single movies, so it's possible that a movie is showing up multiple times in this data set if it's nominated for multiple Oscars. Now, it did filter down on what types of Oscars we're considering here, so we're not considering any Oscars that can only be won by a single genre. We're not considering the best documentary or the best animated film, because that would obviously skew towards a single genre, but I have not filtered down, so we might have duplicated movies in here, so that's worth keeping in mind about whether this data is actually good enough to answer the question that we want to answer. But we've estimated our winning probability, and now what we're going to do is we're going to compute our expected counts of our winners, assuming that this winning probability is the same for each of the different genres. So what we want to do is we take our call sums of our counts winners, and what this is going to do, if I run this, it's going to output the total number that were nominated from each genre. So we're going to say, what if the same number of movies is nominated as what we've actually observed from each genre? Is there a difference in winning percentage based on which genre they were nominated in? And so if there's not, then what we should expect is that there will be 1 minus the winning probability times by the number observed for the losers, and the winning probability times by the number for the winners. So we can define that expectation there. So we compute the test statistic in exactly the same way that we had been doing before, and then we can use our chi-square test here. Now, our chi-square test here, and I should be calling lower tail equals false on it as well. I've written the degrees of freedom as 13 minus 7. Now, we would come to 13 minus 7 if we were thinking about this as a two-way contingency table, right? And the reason is that we'd have 14 total categories. So we'd have comedy movies that win, comedy movies that lose, action movies that win, action movies that lose, and so on. There's 14 of those because there are 7 genres and 2 outcomes. And so then all of those would need a probability estimate for it. And we would get those probability estimates for the first 13, and then we can solve for the last one by using 1 minus the first 13. And then, under the null hypothesis, we would need to estimate 7 different parameters. And those 7 parameters would be the winning probability, so that's what we've written here, as well as the proportion of movies which fell into each of the different categories. And so the way we would have gotten that is we would have taken these call sum winners, we would have divided by the total number of movies that were released, and then that would have given us these 6 different probabilities that a film is any of the different genres, and then we could have multiplied the probability that it's a genre times by the winning probability or the losing probability times by the total number. Now, the way that we've actually set it up here, it implies that we're keeping the sums of the different genres fixed, so the total number of any genre is fixed, and we're only estimating one parameter. So if you want to view it like this, then really what we're looking at are the final type of problem that we considered in the course notes. And in that problem, we wouldn't actually be estimating 13 and 7 different parameters. Under the MLE, we would need to estimate 7 different parameters. And the 7 parameters that we would need to estimate are the winning probability for each of the different genres, right? So there are 7 genres, 7 possible winning parameters. And under the null hypothesis, where we assume that the winning parameters are equal across all models, we would have 1. And I think that's probably slightly more natural to ask the question here. Now, in either of these cases, we can also use our closed form formula to get to this, which is a minus 1 times b minus 1, where a in this case is 2 and b is 7. So that's going to be 2 minus 1 times 7 minus 1. In any event, all of these are just going to give us 6. So there's a few different ways of getting there, and we can run and get our p-value of about 0.278. And so what that tells us is actually that there doesn't appear to be that much evidence against the null hypothesis here, which means that once you've been nominated for an Oscar, your genre doesn't so much matter, or at least that's what these data seem to suggest. Again, these data are not perfect, but that's kind of an interesting pattern. So I have two more examples here, and both of them revolve around hockey, at least slightly. So the first one is we want to know whether the number of goals scored in a hockey game follows a Poisson model. What I have here are a data file that have the scores of hockey games, and you can read that in. And each of these scores is going to have a team's away score and a team's home score. So that's the number of goals scored by the away team, the number of goals scored by the home team. And so what I'm going to do is I'm going to sum up both of those values across all of them and get this total goals vector. And so what this total goals vector is it is the total number of goals that were scored by both teams throughout the different hockey games. Now, if you're interested, you could take a look at these data where you're just looking at the home team or just looking at the away team, and perhaps you might get different results with those. So that could be an interesting way of continuing into the future. Now, in order to fit a Poisson model to the data, we need to find the MLE of theta. And in this case, we're going to find theta hat, and we know that in the Poisson model, the MLE is given by the mean. So I'm going to take the mean of that vector of total goals, which is going to be, I think, approximately 5 or 6. It's 5.6. And so now what we want to do is figure out, do these data appear to be what they would be if this was a Poisson distribution? Now, this next line that I'm doing here is I'm taking all of the games which had more than 10 goals scored, and I'm truncating it at 10. And the reason for this, if I output the table of total goals, you can see that we have between 0 and 15, but as soon as we go 10 or above, we start to see a dramatic fall off in the number of goals that were scored, right? So 10 and 11 both have a fairly high number, but then 12 drops down to 31, and 13 to 24, and 14 and 15 to 5 each. And, you know, we can truncate this at 11 different categories. I think it's most natural to roll them all into 10 here. You could make a slightly different decision, but that's what I'm going to do. And then I want to compute the expected number of goals. So it's pretty easy to find the probabilities of a Poisson distribution in R, because we can use this dPois function here. And so what this dPois 0 to 9 is going to do is it's going to output the probability that a Poisson random variable with lambda equal to theta hat takes on the values 0 through 9. And so right here, if you actually run this code, it's going to output 10 different probabilities from 0 through 9. And then this last one is going to be the probability that it is larger than 9. So that's going to be 10 and above to get that last category. And so if we were to sum all of these probabilities, we can come in here, you should see that they sum up to 1, right? So this is all the probability that it's in 0, in 1, in 2, and then this final one's the probability that it's 10 or above. And if we multiply that by the total number of games that we've seen, or the length of our total goals vector, then that should tell us how many of each different game we should expect to see. So that's the probability that 0 goals are scored in a game times by the number of games, expected number of goals of 0 goal games. So if we take a look at the expected goals, you can see that again we have 11 numbers output here. And just if we want to peek at this quickly for ourselves here, if we look at the table of total goals, which maybe I'll run this next line of code where I define actual goals to make this a little bit easier for us. But if we look at this actual goals variable, you can see that for 0, our expected goals are 23.23, and in reality we saw 220 games with 0 goals. Now, if you watch hockey, you'll know that this is going to be inflated for a number of reasons, and there are some ways that we could clean up this data, but already that should leave us a little bit suspicious of whether or not this is going to work out. Still, we can compute our test statistic just the same way that we've been doing before, And it seems like I didn't actually run this line of code that I talked about for a while up here. So let's do that and then run our actual goals. Now we can compute our test statistic as we've been doing before. And again, here we want to run the p chi-squared. We can set the lower tail to be equal to false. And the degrees of freedom, it's 10 minus 1. Well, under the null hypothesis, we have 11 categories, so there are 10 variables that we would need to, 10 parameters we would need to estimate. Assuming that it's a Poisson model, we just have one parameter to estimate. Or again, you can go k minus 1 minus p. In either event, when we run this, we see that the test statistic returns a p-value of 0, which is exactly what we would expect, as we discussed. Now again, there are some ways that I'd like to clean up this data. If I were to actually want to look at it, I'd want to remove certain games, like preseason games and that type of thing, but perhaps it's interesting to play around with if you're interested in sports. And if you're not, then I'm sorry that the last example is also about sports. And in particular, what I want to do is there is a goalie who plays for the Montreal Canadiens. His name is Carey Price, and people tend to have this idea that Carey Price plays particularly well on Saturday nights. He has a nickname to this effect, and as a statistician, I'm quite interested to know whether the data actually support this claim. And so what I've done is I've downloaded all of the games from his career, which are in this careypricegames.csv file. So we can read that in. Again, what we want to do is make a two-way contingency table here. The first is going to be the day of the week. The second factor is whether or not he won. And so we can take a look at what that actually looks like here. And when we do that, we can see that there are 7 days of the week, 1 through 7, 1 being a Monday, 7 being a Sunday, and false is a loss, true is a win. Okay, so we can see that in fact, he has won 354 of his 354 plus 353 games. So he's won just over half of the games that he's played. And what we want to do is essentially the same thing that we did with Oscar winners here. So we're going to take the row sums multiplied by the losing percentage, the row sums multiplied by the winning percentage to get the expected number, assuming that he wins the same no matter what day of the week it is. And so you can see here would be the expected number of games that he would win, lose, and win, depending on the day of the week. Now we can compute our test, and then we can compute our p-value. Now in this last one, I've used the explicit formula. So again, we talked through the different ways you could think about the degrees of freedom for this type of example here, but I'm just using A, which has 2 levels, minus 1, times by B, which has 7 levels, minus 1. And so if we compute that p-value, we can see it's about 20%, which is not particularly strong evidence against the null hypothesis. And that probably means that the commentators do not really know what they're talking about when they're saying that he plays better on Saturday nights. So with that, hopefully that's some interesting data that you can play around with and see if you can run similar tests. And after this, we'll jump back over to the regular tutorial where I will start to talk about how to determine the degrees of freedom in a little bit more detail. With those examples out of the way, let's talk briefly about degrees of freedom. As a general rule, you can determine the number of degrees of freedom for the LRT-based tests we have been discussing by taking the difference between the number of parameters that need to be estimated under the MLE and the number of parameters that need to be estimated if the null hypothesis is true. It can be helpful to try and get a general sense of what a degree of freedom is intuitively. You can think of degrees of freedom as a question of how many things are free to vary based on what we need to compute with the data. Let's say that we have 10 measurements and that we know that the mean of these samples is exactly 1. Now, I want you to give me a possible set of numbers that fits this description. How many of those numbers do you get to choose? The answer is 9. Why? Well, you can pick the first 9 numbers exactly as you want, but we know that the 10 of them need to have a sample mean of 1, which means that after you have picked the first 9, the last one is determined. In this sense, we can think of there as being 9 degrees of freedom in the data. This is exactly why we take the degrees of freedom in a simple linear regression model to be n minus 2. We have n total observations and we need to estimate 2 parameters from it. To construct a data set that has these parameter estimates, you are free to choose n minus 2 of the data points. Once you've done that, the remaining 2 are determined by the values of alpha hat and beta hat. Now with the chi-squared test, we extend this intuition slightly. We start by asking how many parameters do we need to estimate for our MLE? Then we ask ourselves, if the null hypothesis were true, how many parameters would we need to estimate? The difference between these two values is the degrees of freedom, since it corresponds to the number of parameters which are free to vary under the null hypothesis. If the intuition does not stick, luckily this is a concept which becomes more clear with practice. There are some important things to remember when counting up these parameters. First, remember that the multinomial model constrains its parameters to sum to 1. That is, if you have a multinomial with k different categories, you actually only need to estimate k minus 1 parameters, since the final parameter is estimable by finding the value that makes them sum to 1. This is also going to apply if you are in a situation with multiple different multinomial models. Here, each one only requires k minus 1 parameters, which you can add across the models you are considering. Second, when the null hypothesis posits a constant for those parameters, this does not need to be estimated. If part of your null hypothesis is that theta1 equals 0.5, say, then if the null hypothesis is true, you do not need to estimate that parameter. You know it equals 0.5. As a result, you would not add any of these types of values when counting the null parameters. Note that this also applies when you're testing a hypothesis of, say, uniformity. If we have 5 categories and want to know whether each of the categories occurs with equal probability, this is equivalent to testing each theta equal to 1 over 5. Third, for the common settings, we do have explicit formulae for determining the number of degrees of freedom. These are presented in the course notes. Recording these and having easy access is not a bad idea. This translates the problem into recognizing the general type of test rather than needing to explicitly work out the parameter counts. Still, the idea of differencing between the two totals is one that comes up often in statistics and is far more generally applicable and will work in any situation. With all of that out of the way, let's have a brief discussion about the AstraZeneca vaccine and Stat231. I want to lead with a disclaimer. I'm not a medical professional, and this is not medical advice. In fact, I am going to intentionally not discuss the specific numbers in this video here. Anything that I do express is my own opinion on the matter, and you should certainly consult a doctor before making your own medical decisions. For the unfamiliar, the AstraZeneca vaccine was approved for use in Canada based on the efficacy reported from clinical trials. Following this approval, there were reports which suggested that the formation of blood clots may be a rare side effect of the vaccine. Following this, the Canadian government paused the use of the vaccine in people under the age of 55. So the question for us is, what can Stat231 tell us about this vaccine, the government's decision, and how we can make sense of an otherwise complicated situation? To begin, in an earlier tutorial video, I had used the PPDAC framework to analyze the Moderna COVID-19 vaccine trial. I have not done the same thing with AstraZeneca, but you could, and it would possibly be an interesting exercise. One of the key things to watch out for during a PPDAC is what we can say about study and sample error. In the past video, I had used the concept of study error to illustrate why it is important for us to continue to follow the public health guidelines even once we are vaccinated. The study is run in a population where this is the case, and if we change our target population to be people living without these restrictions, then the results of the study may no longer apply. All of these same caveats will apply here as well. Now, moving beyond the original vaccine efficacy questions, we are interested to determine how Stat231 may be helpful for assessing the possible negative side effects of the vaccine. If we had some time, we could plan a study to investigate these questions, but there are several issues involved with doing this. First, we have ethical considerations to make. If we suspect that blood clots are a major risk, then it is potentially unethical to provide the vaccine to individuals to test this. Second, to have a controlled trial would involve withholding the vaccine from certain individuals in the population. This may have ethical consequences if we think that the vaccine is safe and effective, since these individuals remain at a higher risk for COVID, which we know is a concern. As a result, running a direct experiment for this problem may be challenging. Instead, we are relying on information that has been collected based on the vaccine use out in the world. In Stat231, we discussed that this is a type of observational study, and we mentioned that while it is preferable to use in experimental methods wherever possible, observational studies are often our only recourse in answering questions. The idea is that, to date, some large number of individuals, millions worldwide have already received the AstraZeneca vaccine. We can follow up with these individuals and watch them for adverse reactions and use these data to try and determine whether or not there are side effects which ought to change the way that the vaccines are being deployed. Let's consider this for a moment and see if we can determine why this procedure may not be the most desirable way of accomplishing this task. Think about who has been eligible for the vaccine so far and who was eligible for the vaccines earliest. Generally speaking, priority was given to the elderly or individuals with pre-existing health conditions. Now, we are trying to use these observational data to inform our thoughts regarding whether or not there are negative health effects from the vaccines. Why might this be a problem? This relates back to study error once more. If we want to use the observational study to make conclusions about all individuals living today, then our target population is everyone. However, our study population includes only those who have been eligible for the vaccine, which is certainly not representative of the target population at large. This is one very important consideration to keep in mind. While there are good reasons why it may not be possible to run an experiment on a representative sample, using the data that we have is possibly subject to severe study error. Now, we could dive into thinking through the data quality and possible issues with that in far more detail. If you're interested, you can do this for yourself. But to continue to show how the discussions we have had in this course are pertinent, let's continue forward. For now, I will ignore estimation, as it really is more of a base for some of what is to come, and we can jump into our thoughts on hypothesis testing. If we focus on the question of linking the AstraZeneca vaccine to blood clots, there are a number of ways we could theoretically test this question. This provides a lesson in taking care of how we ask questions. We would need to consider precisely what we are interested in. Perhaps we want to know if the number of people who develop blood clots after receiving the AstraZeneca vaccine is different than the number of people who develop blood clots after receiving the Pfizer vaccine. If this is the quantity of interest, then we would likely want to run a two-sample test, where the first sample are individuals receiving AstraZeneca who form blood clots, and the second sample are the individuals from Pfizer. We would then be interested in testing whether mu1 equals mu2. There would be some concerns with running this test as is, but the general framework seems relevant. Of course, choosing those who received the Pfizer vaccine as the comparison group was an arbitrary choice. We could just as easily choose people receiving another vaccine, or even people who have not received a vaccine at all. In all of these cases, we would be running a mean comparison test, where we let the mean represent the expected number of people who develop blood clots or similar. This is only one possibility. Another would be to consider only those people who have received the AstraZeneca vaccine and then specify a binomial model for these data. Here, theta would represent the probability that an individual develops blood clots. From this model, there are a number of points that we may be interested in testing. For instance, there is likely a risk level that is deemed acceptable for any medical treatment of this form, perhaps 1 in a million or so. We may be interested in knowing whether, based on the data, theta appears to be greater than this threshold, which would correspond to a null hypothesis that theta is less than or equal to 1 in a million. We also may have a similar baseline that could be selected based on previous vaccines, or perhaps we have good estimates for the same risks in the other vaccines in use. Again, here we could run a one- or two-tailed test depending on what is relevant, where theta represents the probability of developing the rare clot. Again, we would need to have the data to properly proceed with the test, and we would want to consult a subject matter expert on the correct level to compare to. Still, running this test is something that we have the machinery to do in this course. Related to this, we also have some capacity to quantify the uncertainty in the estimates. The news headlines all list the total number of people who have developed blood clots, and it lists the total population. This gives us a point estimate. In Stat 231, we discussed numerous ways of expanding this point estimate to an interval, allowing for us to capture how uncertain we are with these specific values. This is something that is likely worth reporting alongside the proportion. If we did not want to use a comparison of means or a binomial proportion test, we could also turn to our chi-square test. Here, there are numerous ways we may construct this test, again based on the underlying medical science. The obvious way from what we discussed in this course is to consider a two-way contingency table. One of the factors would be received the AstraZeneca vaccine, and the other would be developed a blood clot. Then we would want to test the hypothesis of independence. There are probably countless other ways that we could test interesting hypotheses based on these data with the tools in this course. My primary point here is twofold. First, when approaching a statistical problem, we have to be careful to define what we mean very specifically. It is not enough to ask the question, is the vaccine related to blood clots? We need to be more specific and clarify in what way are we interested whether the vaccine is related to blood clots. Second, the tools that you have acquired in this course can form the basis for the analyses. A practicing statistician working on these problems would likely apply more nuance to the questions at hand, but fundamentally the techniques that you have learned could form the basis to answering the questions that we have been posing. Where does that take us? Well, if we had the data, we could pick our relevant hypothesis test and run it. We could compute a p-value. We could use the guidance in this course to see what evidence that p-value provides for us. Now, let's hypothetically say that the p-value provides very strong evidence against the null hypothesis, whatever that happens to be, such that we can be pretty confident that AstraZeneca vaccine is more strongly linked to these blood clots than would be acceptable. Let's say that the p-value we compute is far less than 1%. What does this mean? Well, throughout the course, we have tried to stress that the size of the p-value does not tell us the size of the effect. That is, if we know the p-value is very small, we do not know that the vaccine is far worse than we would expect, just that there is strong evidence that it is worse. This is where we would bring up the idea of practical significance as compared to statistical significance. In this case, the distinction between practical and statistical significance is very important. Statistical significance answers the question, is there a difference between acceptable rates of blood clots and the rates if you receive the AstraZeneca vaccine? Practical significance, on the other hand, answers, does this difference actually matter? With a p-value that is far less than 1%, most people would agree that we have reached statistical significance. However, this p-value tells us nothing of the size of the difference. Let's say that the acceptable rate of this type of blood clot is 1 in a million. Our p-value only tells us that we have strong evidence against the rate being 1 in a million based on the data. But what if our data suggest that the true rate is 1.01 in a million? It is completely possible, depending on the specific data we have, that we could compute a very small p-value with this as our estimated rate. Now, it seems unlikely that this rate would be deemed practically different when compared to the base rate of 1 in a million. And this is an important distinction to hold in your mind, one which you can understand completely based on the tools of this course. As with any of the topics we have discussed here today, there are plenty of other ways that we could keep pressing the tools of the course to answer these questions. I'm sure that you can think of some that I have missed here. For instance, there are ways that we could incorporate Gaussian response models here as well. It would require a little more creativity than what we have done so far, but it certainly could be done. What's more, the most natural type of model to apply to these data, a logistic regression, is a topic that you'll learn about in fourth-year stats courses that directly expands linear regression to data that look like these. I hope that it's interesting to see how the tools we have been discussing throughout the term are all pertinent to the real world, and how even one problem can span a number of them. There's one further concept which is particularly relevant to the discussion at hand, and that is about establishing causal relationships. We have circled around this point slightly, for instance when we were talking about the use of experimental versus observational studies. However, we can ask this question more directly. Does the AstraZeneca vaccine cause blood clots? As we have discussed, this question is much more difficult to answer than the ones which we have been considering until now, especially given the observational nature of the study. We can consider some ways that may help or hurt our chances of being able to make a causal determination from this study. We have already discussed the concerns related to study error, that the people who have received the vaccine are likely to have more health risks than those in the general population. This already leaves us with the requirement to ensure that any conclusions we make are made with this in mind. In particular, our conclusions should always be limited to the members of our study population. As a result, perhaps a better question is, does the AstraZeneca vaccine cause blood clots in members of the population who are at elevated enough health risks to have qualified for vaccination so far? Is this a question that we can even hope to answer with these data? The answer is maybe. I am not aware of the exact policy for how vaccines were assigned, but that will be key as to whether there are any lurking variables which may be confounded with the outcome of interest. That is to say, the way in which it was decided whether someone received the AstraZeneca vaccine or any of the other approved vaccines will help to determine whether we have the capacity for causal conclusions. Let's consider two hypothetical vaccine schemes, random distribution versus regional distribution. We can think of a random distribution scheme where, when someone arrives at the vaccine center, the particular vaccine that they receive is chosen randomly from the possible vaccines. That is, it is not decided in advance at all. If this is the case, then this randomization provides us with a very powerful place to start. The reason is that if the vaccine that anyone receives is not related to other factors about them, and if we have a large enough sample of people, then any possible lurking variables can be thought of as having been taken care of by randomization. Any differences in people's propensity towards blood clots, for instance, should be approximately equal between the various vaccines. As a result, we can use the groups of individuals who received another vaccine to begin to answer questions of a causal nature. What if, instead of random distribution, the types of vaccines were distributed based on region? That is, what if every vaccine center received one of the available vaccines to distribute so that the region that a person lived in predicts the vaccine that they receive? As soon as we see a regional divide, this should make us pause when trying to conduct causal inference. The region in which someone lives is oftentimes related to other relevant factors, especially factors related to health. What that means for us is that it's possible that the AstraZeneca vaccine could be distributed to regions that have individuals with a high propensity towards blood clotting. Then, if we happen to observe a statistically and practically significant difference in the rates of blood clots, we cannot be sure whether this difference is due to the vaccine itself or whether it is explained because of the regional differences in who received each of the vaccines. For epidemiology, the course notes discuss a number of necessary conditions to determine whether an observed association is causal. The association must be observed in many different studies, it must remain present when possible confounders are taken into account, it must have a plausible scientific rationale, and finally, the response must be consistent. My focus has been on whether we would be able to determine the second point, whether we'd be able to take account for all possible sources of confounding based on the study, but a similar discussion could be had for each of the above points. Have we seen sufficient evidence across different studies of the vaccine to feel as though a causative effect is likely? Is there a likely scientific rationale for the blood clots would form? Do we see an increased prevalence in blood clots with the vaccine always? These are questions that I do not have the answers to, at least not directly. These are also questions which are not easy to answer, and the individuals responsible for making decisions regarding vaccine deployment have a challenging job. It is a high-stakes decision in both directions. If there really does exist a meaningful causative effect between the AstraZeneca vaccine and the blood clots, it is important to know this and take the necessary precautions. If the effect is not significant, either statistically or practically, or if the effect is not truly causative and instead is the result of an unmeasured confounding relationship, then withholding the vaccine is a potentially very dangerous choice. There's a lot that goes into making this assessment, both from a subject matter and a statistical perspective. I hope that seeing how these concepts can be approached based on the ideas that we have been showcasing this term gives a sense for the importance of these ideas. Even if you never end up taking another statistics course, I hope that this provides you some ability to critically think about these types of studies and the conversations when they happen in the future. Now, if you want my opinion, I mostly agree with everything that was written in the Piazza post. I am excited for whenever I qualify to be able to take a vaccine, and I hope that that is soon. I recognize that there are risks in my everyday life, and if I had to guess, I would suggest that my risk of a negative health outcome from receiving the vaccine is probably lower than my risk of a negative outcome when I'm driving to or from the vaccine site. Again, I have not seen the literature on this, and I'm not a medical scientist, but from my own personal perspective, based on what I have seen, that's where my brain is at right now. But I hope that the tools that we've given you will allow you to make an informed choice for yourself. And with that, I will end the content of our final tutorial of this semester. I hope that this has been informative for you and that you have managed to gain some value from these tutorials. I have had a lot of fun making them this term. If you have any feedback for me in particular about the tutorials, especially if you made it this far, I would love to hear from you. Please feel free to send me an email if there's anything that you would like to say, whether there was anything that worked well or did not work at all. I'm very happy to hear from you. Further, if you have any questions leading into the exam, please feel free to reach out. I'm happy to provide whatever guidance that I can for you in that regard. Thank you all for the wonderful semester, and best of luck on the final.